I begin this video with a bit of a warning. This is going to be fairly long and complicated, so you're probably going to want to watch this video multiple times. The topic is on the hierarchical test of significance for a moderator, but really what I'm going to do is I'm going to go through this whole concept of hierarchical testing and interpreting B's. So again, this is going to take me a little bit of time. And what I'm going to do is I'm going to start out with constructing data as I've got an x1 and an x2, and then I create an interaction term, which is basically just multiplying my two primary predictors, x1 and x2. Now, to give you some idea about my x1 and x2, x1 is a continuous variable and x2 is a binary variable. So therefore, x1 and x2 is a combination of the two, they're multiplied. And then I create a dependent variable that is a function of x1 and x2 and the multiplication of x1 and x2, and then I add some random normal noise or error. And then I create a data frame, and that data frame is what I'm going to distribute to everybody. Excuse me. And just so that you can see what the correlation matrix looks like among my predictors, let me just split this a little bit differently. That way we can see the whole matrix. I rounded it to 2 digits, and as you can see here, we have a pretty strong correlation between x1 and y, a pretty strong correlation between x1 and my interaction, so we have 0.78 and 0.72, and then we have a negative correlation between x2 and x1. It's slight, it's minus 0.2. And then if you take a look at the correlation for y, we have pretty good prediction for x1, pretty weak for x2. But the correlation is about 0.1, and then it's almost 0.8 for the interaction term. Okay, so what I want to do is I want to step through a very simple sequence of models. And so I run all 3 of these models, and let me explain each one of them. So HT, it's just HT is hierarchical test, and 0, 1, 2, 3, those are the different steps that I want to take. So the first model, all I'm doing is testing the intercept, and that's just seeing whether there is overall there's a significantly different intercept or different grand mean than 0. Uninteresting. The first one is I use x1 as a predictor. Okay, the second model I use x2 as a predictor. So my second model has x1 and x2 in it. My first model just has x1. So I have a bivariate relationship, and then I do multiple regression in HT2. And then HT3, as you recall, I use this asterisk, which is essentially an expansion operator. So it gives me both the main effects as well as the interaction. And it's a shortcut for having to type a lot. And as many of you know, I'm kind of lazy and I prefer not to type a whole lot. So now I have these 3 models, and what I can do is I can test them for whether there's a significant difference between each of these steps. Okay? So the first one, my first model, this is just my intercept only, and then I'm testing whether there's a significant main effect, and then I'm testing whether the second predictor is a significant predictor, and then third is I'm testing whether incrementally whether there's a change in R squared that's significant by adding the interaction. I can get something similar if I just look at HT3. And what I'll do is I'm going to expand this up so that we can see all of the output, or at least a reasonable amount. And you'll notice that this effect here, 2.43, is the same as testing this effect here. So what I'm doing is I'm testing the differences, the change in R squared, between having a main effects only model, that's this one, remember, because all I tested in model 3 was main effect of x1 or x2, right? Remember that plus sign is an or, a logical or. In my fourth situation, my fourth model, I'm testing the interaction. So I'm testing the main effects and the interaction, which is summarized in this table right here. So this model is what I'm comparing in this, because this one is testing whether there's a significant difference between this model and the previous model. And that significant difference is just by adding in the interaction term. Okay? So oftentimes people will claim that that is the hierarchical testing of our model. But let's take this a step further. Suppose, by the way, I can test the order of the models in any way, and this one I just flipped around, and you can see I still get a significant effect, 2.43 times 10 to the minus 8th, which is the same as right here, 2.43. These are just p-values that I'm looking at. Okay. So now, if these are hierarchical, we would assume that there is some hierarchy, not just to the testing, but also to the parameter estimation. And that would be incorrect. So the reason why I want to show you, I want to step through this, is I want to show you that here what I've done is I've used the expansion operator, for HT3. And then down here what I've done is I've explicitly modeled the interaction term as a product of x1 and x2. And when I calculate these two, okay, you'll see that the effects are identical. Okay, so I get 5.28, and you'll see here, let me see here, I get, oh, I'm testing different things here. This is easier. Okay. So if I look at my coefficients for whether I specify a multiplicative term or an interaction term, they're identical. These are my coefficients. So this is my coefficients for specifying the interaction. Notice the semicolon, the colon there, and this is the coefficients for when I specify a multiplicative term. So in terms of a linear model, it really doesn't differentiate whether you say that it's an interaction or that it's just another predictor. There's no differentiation at all. So if there's no differentiation, they're identical, how are these tests hierarchical? Well, they're hierarchical for many reasons. One is when you're testing, let's go to, this is instead of looking at the ANOVA, I'm going to look at the regression results. When I test for just main effects, so let me give you a summary for H2, because these are just two main effects. Okay, and if I ask for the coefficients for HT2 and I ask for the coefficients of HT3, let's just compare what these coefficients look like. So here we've got a differences in intercept, albeit slight, it's about by 0.1, but that's immaterial. We have a difference in our coefficients for x1, we have a slight difference in coefficients for x2, and of course we didn't have a coefficient for our interaction term. Additionally, we also have different p-values. So if I look at the summary for just my main effects model, I have p-values that are associated. Now, granted, they're significant, but they are different p-values here than I would get when I do my summary for HT3. So let's compare them. So my intercept for my full model with my interaction, the p-value is 0.21. Okay, for this one, it's 0.58. Okay, just the main effects. So the p-value differs for the intercept. We already know that the coefficients differ from for the intercepts and between the two models for the intercept, as well as for the coefficients of the main effect. So the main effect coefficients change, but the p-values also change. So the p-value here is for the full model is 5.28 times 10 to the minus 10th. And in this case, for x1, it's 2 times 10 to the minus 16th. So what happens is our p-values and our parameters change when we include the interaction term. So what is that telling us, and how do we interpret all of this? Well, it's telling us a lot. First, it's telling us that the parameter estimates are contingent upon the parameters that we enter in our model. Now we know this. We know this from what we talked about before when we were just looking at multiple regression. That multiple regression, when we have any collinearity among our predictors, that what we're going to do is we're going to get partial regression coefficients. And those partial regression coefficients extract out the term of our parameter as of our shared variance between our predictor that is not specified in our parameter and our dependent variable. Remember that what we're doing is we're taking out the part of any other predictor that's not relevant for the parameter estimate that's focused on. So remember back to our Venn diagram that we're taking out any shared variance that's not attributable to the focal predictor and the dependent variable. So anytime we have collinearity, that collinearity leads to changes in the regression parameter coefficients, okay? Because instead of being, say, bivariate coefficients, they are partial R's. Well, the same goes for regression. That when we're estimating these things, we're estimating these parameters, and they are going to be contingent on what variables we include. Now, one of the greatest concerns by many people is that by including an interaction term, we frequently have situations in which multicollinearity goes up and goes through the roof, right? Well, multicollinearity can be easily handled by mean centering of our predictors. So what I can do is I can mean center our predictors, and when I do a correlation coefficient, you'll find that the correlation coefficient is identical. Remember, x1 and y was 0.78. X1 and our interaction term is 0.72. All of these correlations are the same. So all you have to do is scroll back up here. Our correlation matrix is way back up when we began. And it is an identical correlation matrix, and I assure you that I did indeed center these. These are mean centered, and what I did is I mean centered the interaction as well as my two predictors. Now, why would I mean center them? Because mean centering does away with any of the metric differences, and by doing away with the metric differences in terms of the means, what we do is we eliminate some of the collinearity that may arise. But as you can see from the correlation matrix, there's almost no change in the multicollinearity or the relationship among our predictors and our interaction term. But that is the method in which we can reduce multicollinearity. Nevertheless, when we are testing for these effects, we are going to get different parameter estimates between a main effects only model and a moderation model. And why is that? Well, first is when we have a main effects model only. That's HT2. And so if I go back to a summary of HT2, I am getting partial correlation coefficients right here. But partial correlation coefficients do not take into consideration the potential effects of the interaction. So when I include the interaction term here, I'm getting different parameter estimates for both of my primary predictors. I went from 1.7 or 1.8 and 0.9 to 1.1 and 0.95. Now, why is that? Well, in this case, these are partial R's, okay, or they're partial correlation coefficients. If I corrected for the metric, I could get partial correlations. But now these are no longer partials. These are very interesting and somewhat difficult to interpret parameter estimates. So bear with me when I discuss this, and this is related to centering. Part of the reason why we center variables is that we try to move the metric of our predictors within the range of our prediction model. So remember back to some of our assumptions that we discussed in previous weeks, that one of the discussions was that the observed range of values was representative of the values of which we were interested in predicting about. So what we didn't want was a misrepresentation of our prediction model where we use certain values, a restriction of range of our predictor values, to then extrapolate to values that we had not observed of our prediction for our predictors into a realm that we would, we'd probably not be terribly safe in extrapolating to. Well, when we mean center, what we're doing is we're taking the mean out of each one of our predictors and we're centering the regression equation around 0. And so therefore we have interpolation rather than extrapolation. So that's one. But the second thing is, and this is relevant to interpreting these B's, is that x1 and x2 in this context right here, that these parameter estimates are the parameter estimates assuming that the other predictor equals 0. So let me be concrete about this. x1 has a b of 1.1 with y when the value of x2 is 0. Similarly, x2 has a b for y when x1 equals 0. And so therefore these are conditional regression parameter estimates. And these conditional regression parameter estimates become exceedingly difficult to interpret unless the metric of each one of these variables, these predictor variables, has 0 in the range. And so by mean centering them, we are centering the values of our predictors around 0. And remember that when you think about estimating our best guess for any value, the best guess always centers around around the mean. And by centering the whole distribution around 0, we get the most interpretation of each, probably the easiest, but the strongest interpretation of these regression parameters when we assume 0. So this is I know kind of a circular discussion about this, but what we really want to do is we want to be careful when we're running regression models that we run the regression model according to values that are directly interpretable. And so let me just show you what happens when we do center these values. Okay, so I'm running the same models that we ran before. All the p-values are the same. Now what we have is we have parameter estimates here where the intercept is 0.5, the b parameter is 1.8, or excuse me, b1 is 1.8 and b2 is 0.9. So b naught is 0.5. So we have 0.5, 1.8, and 0.9. Then when I add in the interaction, I get 1.8, 0.9, and now the intercept changes. Okay, so what we're getting is, because these all include 0 from the beginning, they're easier to interpret and they don't change a whole lot between including the including the interaction and excluding the interaction. So the two models don't differ a whole lot. And you'll also see that the coefficients don't change a whole lot, because if I do ht2.c and ht3.c, you can see that the intercepts change, but for the most part the b parameters are pretty close to one another. So therefore we still have partial regression coefficients. They're slightly different, but in this magnitude of difference we don't really pay that much attention in social and behavioral sciences. In fact, most of our attention is paid to just whether the p-value is less than 0.05, and then we wax eloquent about why our model is certainly a good reflection of our underlying theory. So in summary, what we've covered here is what the hierarchical tests of significance for moderators really means, how these tests are performed, and that they're not hierarchical in the sense that I've discussed previously about type 1 sums of squares hierarchical, because we can talk about that later. They're hierarchical in terms of x1, an interaction is tested as an incremental change in the R square between a model with the interaction compared to a model without the interaction. And that's what I showed you here in these ANOVA models. And I'll just run this again because this is a nested model comparison. A nested model comparison calculated in an F-test. Same F-test that you saw in Cohen and Cohen, West and Aiken. And this F-test is easily replicable in Excel. You can just test the differences in R squared, and the differences in R squared is easy to assess. And this effect right here, this p-value, is the same p-value, 2.43 times 10 to the minus 8th, that you get from testing just the interaction alone in the model. It's 2.43 times 10 to the minus 8th. So what you're seeing here is the p-value here does indeed reflect the significant contribution of the interaction above and beyond the main effects. So that's how it's hierarchical. It's hierarchical in the sense that it is an incremental gain in R square from a model without the interaction. In this case, this is a very simple single moderated effect. So it's a test of whether with the interaction versus without the interaction, and that p-value, that's the difference between these two models, is reflected in the F-test, or the probability test, and the t-value associated with the interaction. Okay, so as I warned you before, that this was going to take a while. Now, why is all of this relevant? Well, this is relevant in the next step when we're going to start talking about plotting interactions and understanding how interactions occur, and also how to interpret the B's. That so far what you've learned is that the B's change from a main effects only model to an interaction model, and they change because of reasons that have to do with scaling. When we center, we can do away with the scaling problems and have parameter estimates that are pretty much the same, so we get partial correlation coefficients. But that those changes also are reflected in a logic underlying the parameter estimates. That in our main effects only models, we have predictors that are interpreted according to the partial correlation coefficient logic. When we have interactions that are included, those parameter estimates change because by including the interaction, those main effects now are assuming that there is the value of each one of those predictors is 0. And when we assume that it is 0, what we are doing is we are assuming a certain level of another variable when interpreting that coefficient. Now, we haven't had to do that before, so that's why things change a little bit. So again, the hierarchical test, it can be done by nested model comparisons or testing the individual interaction term. And just for those of you in SPSS, I ran this in a program called PSPP, and this is the output. And you're going to see exactly this using the data set. You'll be able to replicate it. So you can see here that I get all the same parameter estimates that I got originally. My original model was summary HT3, and I'll show you that indeed that is true. So here are my coefficients. These are my B's, 1.9. I'll even get the standard errors, why not? Okay, so you can see 1.9, 0.15, 1.1, 0.16, all of these p-values, all the t-values. Statistical packages don't differ a whole lot in that regard. So we have pretty much the same effects no matter what stats package we're using. This is all fine and good. The difference is that in SPSS and in PSPP, they give you the beta coefficients as well as the B's. Remember, in R, we can calculate this if we scale all our variables. Okay, so sorry to go on for so long, but 25-minute video, you should watch this multiple times. So thanks, stay tuned. I'm going to give you a little bit of a revisitation to sums of squares types. Okay,